As the threat landscape continue to evolve rapidly, safeguarding the operational technology has become more critical than ever. As today, we will explore the key principal architectural component and the best practices that can help an organization to build resilient and future-ready ICS infrastructure. So first of all, let's understand why the security of ICS is critically important. In an ICS environment, a cyber incident is not just about a data being stolen or a workstation is going offline. These systems directly control physical, real-world industrial processes. When someone goes wrong in the ICS, it is not limited to digital disruption. It may damage equipment, cause unplanned shutdowns, interrupt critical services, and create continue conditions that threaten the safety of a personnel on site. In severe cases, problem in industrial system can ripple outward, affecting entire community region that rely on essential services such as water, electricity, fuel distribution, and transportation. This is why ICS security operates with completely different mindset compared to the traditional IT security. In IT environment, the primary objective is protecting the data, ensuring its confidentiality, integrity, and availability. But in ICS, the top priority is always protecting the physical operation, preventing safety and maintenance and stable output. Data loss is a concern, but it is secondary compared to the risk of equipment damaging or the operational disruption. So the consequences in the OT environment are far more immediate, more concrete, and more often severe. A single faulty command or unauthorized logic change can affect real machinery in real time, meaning the cybersecurity become inseparable from the process safety and the operational reliability. Okay, sorry. I have to be on the screen. Sorry guys, I'm just stuck with my presentation. Yeah, sorry. So let's discuss the evolution of the ICS environment first. So as you all know that the over a past couple of decades, industrial control system environment have undergone significant transformation. What were once isolated purpose-built system dedicated solely to run the critical infrastructure, such as the energy production, water treatment plant, manufacturing line, oil and gas operations, and transportation network, have evolved into highly interconnected digital ecosystem. Originally, these systems were engineered with clear priority, reliability, stability, and uninterrupted operation. Cybersecurity was not a design requirement because ICS network operate in physical isolated environment with a minimal external exposure. That reality has changed dramatically now. As organization integrating modern technology, the traditional air gap has all but disappeared. This evolution brings a tremendous operational benefit, but it is also introduced a wide range of the vulnerabilities. The attack surface expand, legacy system face threats they were never built to withstand. The adversaries now have more pathway than ever to target the critical operation. Understanding this shift is essential and will help you strengthen your ICS security posture and adapt to this new rapidly evolving threat landscape. So let's move on and have a look on the earlier ICS architecture. In the earlier or the legacy ICS environment, the network architecture was typically flat, meaning all the devices existed on a single unsegmented network with no meaningful barrier between them. In these setups, PLC, HMI, historian, engineering workstations, and often operator terminals are operated within the same broadcast domain. This meant Any device could communicate directly to any other device without any restrictions. Use of a shared credential across multiple systems was a common practice, which eliminated individual accountability. There is no way to trace who made configuration changes, execute command, or access a critical device. On the other hand, these environments relied heavily on open industry protocol, such as Modbus, DNP3, and Profinet, that were never designed with the security in the mind. A Genie laptop often plugged directly into the control network, providing full access to the PLC or a programming or troubleshooting. While convenient for the operation, this created significant exposure, as any compromised laptop or a device connected to the network had unrestricted reach across the entire environment. The lack of the segmentation meant any compromise could separately extremely quickly. Malware, ransomware, or the unauthorized software could move laterally without encountering any access control. Even a simple network scan, a very commonly used in the IT environment, could overload or disrupt the sensitive controller. So this kind of the architecture is highly vulnerable to the type of attack we have seen historically, where malicious codes or the unauthorized logic change propagate unchecked across the controllers. Incident like Stuxnet's demonstrate how easily malware could move through a flat industrial network, reaching sensitive control devices and modifying their behavior. Even unintentionally human errors, such as uploading a wrong project file or executing a scan utility, could cause widespread operational disruption. So in a summary, flat ICS network provide convenience and simplicity, but come with significant risk. Without segmentation or isolation, the entire environment becomes single point of failure and highly exposed both at cyber attack and accidental misoperations. IT OT convergence. So where the organization is gaining significant value, uh, business efficiency from IT OT convergence, but this also expand the attack surface in a way that must be carefully managed. Traditionally, OT systems such as PLCs, SCADA servers, and field devices operated in isolated and focused solely on running physical process. IT system, on the other hand, handle business operation, data analytics, and enterprise applications. Today, that separation has largely disappeared. Modern industry operations rely on IT capability like cloud services, data analytics, centralized monitoring, and remote vendor support to improve the productivity, reduce the downtime, and optimize decision making. This integration delivers major business benefits, such as the real-time visibility, productive maintenance, streamlined workflows, access across the entire organization. However, alongside the benefit, the same connection introduce a new risk. Business network, cloud platforms, remote access tools, and the third-party vendors pathway intersect directly with the operation system. Every one of these touch points become a potential entry point for the attackers. A compromise in the IT environment can now move laterally into the OT, where the consequences are far more severe because the physical process safety and the critical services are at risk. Understanding the importance and the impact of the IT/OT governance is essential for designing the secure ICS architecture, balancing business efficiency with the operation safety and resilience. So, as the IT/OT convergence is happening in many ICS environment, The organization began taking steps toward the security by introducing basic controls, but the architecture still remained significant risky. Typically, typically the first improvement in the addition of a firewall between IT OT, which provides some boundaries protection. However, inside the OT environment itself, the network often remain mostly flat. PLC, HMI, historian servers, engineering workstations still share the large broadcast segmentation with a very little separation based on their functionality and the criticality. Some environment introduce VLANs, but these are often used only for the logical grouping, not aligned with the proper zone-based security model. As a result, VLAN may give you appearance of the segmentation without restricting communication in a meaningful way. Traffic still flow freely between devices because no enforcement point like firewalls or the cross control rules exist between the VLANs. During this transitional period, remote access to the vendor is usually enabled, often by through a VPN or a remote desktop procedure or the RDP, but the security control around it was weak. This creates a highly risk point, especially when a vendor access is allowed directly into the operational network. And because the internal segmentation is only partial, organization may mistakenly believe that the environment is protected, even though the large portion of the OT network are still fully reachable from a single point of entry. Monitoring was introduced, but it was typically IT centric and does not understand the industrial protocol or the control behavior. This means the system can detect general network anomalies but remain blind to the type of unsafe OT specific activity, such as unauthorized logic change or a suspicious function code usage that truly matter in the industrial environment. Because of these gaps, the environment remain at high risk. The lack of the internal segmentation means that once inside attacker cannot move freely across the OT system without encountering resistance. So in a summary, if we discuss this transitional stage mark an improvement of a fully flat network, but significantly risks remain. Security controls exist, but they are not yet significant to prevent lateral movement, remote compromise, or misuse of the industrial devices. It is necessary to step into the journey, but not yet truly defensible architecture. So let's have a look. What is the key difference between the ICS and IT? As IT and OT environment continue to converge, the one of the biggest difference between ICS and the traditional environment is the priority placed on the system availability. In ICS environment, equipment often need to run continuously, sometimes for decades, without interruption. Shutting down for frequent updates or the patch simply isn't an option because it cannot halt production, dis- disturb critical services, or even create safety risk. So when we compare ICS environment to the traditional IT system, one of the most important differences is how the confidentiality, integrity, and the availability is prioritized. In IT, confidentiality often comes first because the main goal of the is to protect the data. But in ICS, the order is reversed. Availability is the topmost priority because the industrial process must run continuously. In ICS environment, system that may operate for 10, 20, or even 30 years without any interruption. Many of these devices use proprietary or the legacy protocol that never designed with cybersecurity in mind because they cannot be patched or upgraded frequently. they remain vulnerable to the modern threats. This makes it harder to maintain integrity, ensuring that commands, configuration, and the process data are accurate and trustworthy. Confidentiality still matter in ICS, but it is not a primary driver. Protecting sensitive engineering data, network diagram, operational parameters is important. Yet the biggest risk comes from anything that disrupts the physical process or alter system behavior. So all of these factors shapes how we design the ICS architecture. Instead of relying on a rapid patching or a traditional IT controls, we need to focus on layer defense, strong segmentation, controlled access, and monitoring strategies that respect the operational realities of the industrial environment. The goal is to maintain the availability, preserve the integrity, and protect the confidentiality with keeping the critical operations safe and stable. ICS threat landscape. So, what is the ICS threat landscape? Is it real or just a hypothetical? Well, the threat landscape facing ICS environment is no longer hypothetical or something we talk about in theory. It is real, active, and evolves quickly. Today, we are dealing highly capable of nation-state actor who target critical infrastructure for strategic or geopolitical purpose. We also seen ransomware group aggressively expanding into the industrial environment, aiming to disrupt the operation and extort the organizations. And we cannot overlook inside threat, whether intentional or accidental, because the people with the legitimate access can still cause significant harm. Another growing concern is the supply chain compromise. Modern ICS environment depends on complex ecosystem of vendors, integrators, softwares, updates, and third-party components. In any part of that chain is compromised, attacker can gain access long before the system is even deployed. So all of this reinforce a key point. ICS security must be proactive, layered, resilient, because the risks are diverse, sophisticated, and increasingly targeted at the physical process that keep critical operations running. So let's have a quick few real world examples from the past. So, so as we discussed the previously, the threats facing ICS environment is no longer hypothetical and something we talk about in the theory. It is real, active, and evolving quickly. So there is a few examples from the real world incident, like Stuxnet, Triton, the Colonial Pipeline attack, and the Oldmere water plant intrusion. Shows just how far attacker can go when our ICS environment are not properly secured. These even demonstrate the cyber attacks on the industrial system are not limited to stealing the data. They can directly manipulate the physical process, disrupt the essential operations, or even target safety system, which is designed to protect the people and equipment. So Stuxnet reveal how malware can alter the control logic to damage a physical equipment in the nuclear facility. Whereas the Triton show that the attacker can attempt to disable or manipulate a safety instrument system. Colonial Pipeline, on the other hand, highlighted how an IT compromise can force a shutdown into IT due to operational independency. And the old Mar water plant attack demonstrated how weak remote access control can allow unauthorized user to alter the chemical dose in a real time. Each of these incidents teach us that the threats are real and reinforcing why the ICS security must be built on strong architectural foundation that protect both digital assets and the physical processes. So because Before further moving forward, we have a quick poll just for the engagement. So I would like to request Mona if you can initiate the poll. So I would like to request all of you to please quickly participate in this so that we can move quickly to the next slide. Maimuna, are you with us?
Yes. Can you see the screen with the poll?
Not yet.
One second. We have 73% people voted. We will wait one more minute.
Oh, yeah, sorry. I'm really sorry. It was on the another screen.
Okay. Let me know when you want me to turn this off.
Sure. Ten, 30, 60. 4. So out of 90% people voted so far, and as expected, we can still see some flat networks. Firewall between only IT OT is at 30%, and full IDG DMC's implementation is about 60%. So you can imagine about 40% is still we are behind the current situation. Okay, Mamuna, that's fine. That's fine. We can move forward. So what is the secure ICS architecture? Let's have an overview first. A secure ICS architecture is built on 4 main pillars: defense in depth, zero trust for the IoT, segmentation and zoning, and continuous monitoring. These pillars collectively enhance the resilience and the reliability of the operational environment. A secure ICS design typically starts with the defense in depth approach, where multiple layered security such as the parameter firewall, intrusion detection systems, and endpoint protection are deployed to delay or detect the threats. For example, a firewall at the OT parameter layer may block the unauthorized remote access attempts, while an IDS monitor the traffic for abnormal Modbus and DHCP commands. Zero trust principle reinforce this protection by requiring strict authentication and authorization for every connection. For instance, a maintenance laptop must be authorized through multi-factor authentication before accessing to a PLC programming interface. Network segmentation is also a key pillar of the secure ICS architecture, spreading the corporate IT network from the OT network with a DMZ and the further isolation safety system or a critical PLC into a dedicated VLAN. Minimal lateral movement and ensure that any compromise is confined to a smallest possible domain. For example, historian and the HMI operate in a separate network zone to prevent a compromised HMI from directly reaching to the control devices. And finally, the continuous monitoring provide a real-time visibility using the tools such as the same platform, OT-specific anomaly detection systems, log collectors. These systems might detect unusual write command to the PLC, unexpected firmware changes. So altogether, These controls create a robust ICS security architecture capable of meeting modern cyber threats while supporting the stable and reliable industrial operations. We will go through about these principles in detail later in the session. So let's move on to understand some security principles. These foundational security principles shapes every uh, architecture and configuration decision within ICS or the OT environment. Least privileges ensure that every user, device, or the process is granted only the minimum access necessary to the platform. It functions, reducing the potential impact of the misuse and or the compromise. For example, an HMI operator may have a permission to view process data, but should not have the ability to modify the PLC logic. Similarly, a vendor remote access account may be restricted to a specific VLAN containing only the equipment that maintain. By minimizing the unnecessary permission, we significantly reduce the blast of radius if account or a device is compromised. Verify every connection. Zero Trust remove the old assumption that everything inside the industry network is trusted. The principle shift to never trust, always verify. Every user, every device and request should be validated, whether inside or outside of the OT network. Every communication path must be authenticated and authorized. For instance, if an engineering laptop connects to a PLC, the connection must pass through a multi-factor authentication or a certificate authentication or a protocol whitelisting before command are accepted. Even a machine-to-machine communication, like a SCADA polling a remote RTU, should be validated through a secure signed traffic. Visibility before the control. Emphasize that the effective security begins with complete awareness of full asset and the communication flow. Without knowing what device exists and what firmware they are run and how they communicate, it is impossible to implement reliable protection. For example, a passive network monitoring tool can map PLC HMI traffic, detect unauthorized device plug into the switch, or identity behavior abnormal identify abnormal Modbus write commands. Only after gaining full visibility, security controls like segmentation, access rule, or anomaly detection be applied correctly and safely. Layered security or the defense in depth ensure that if one safeguard fails, another remain in place to prevent a slow an attack. As discussed previously, a parameter firewall to block the unauthorized external access and internal IDS to detect the suspicious OT protocol activity. Host-based align list on a Genie workstation to prevent malware execution, and physical access control to restrict the entry to the control room. Each controller complement to other, create redundancy and resilience. Ultimately, all of these principles tie back to the visibility. You cannot secure the asset, network, or the process that you cannot identify or observe. Understanding this environment is a prerequisite to designing and enforcing effective ICS security. Zoning. ICS ISA 62443 introduced a structured zoning and contour model that help the segment and industrial environment based on system criticality, operational function, and required security levels. The zoning model is fundamental to build a secure and a resilient ISS architecture. The enterprise zone includes the corporate IT systems such as email, ERP platforms, and business application, which must remain isolated from the OT network to prevent a common IT threat from reaching industrial assets. DMZ, demilitarization zone, act as a secure buffer between IT and OT environment. System placed here such as patch server, historian, and remote access gateway allow data to flow in a controlled manner while preventing direct IT-OT connectivities. The operational zone hosts the system that supports the plant operations such as the SCADA servers, asset management platform, and engineering workstation. These systems require strict control than the IT environment because they directly influence the plant supervisions. The control zone contains the core automation component, PLC, RTU, DCS controllers that execute real-time controller logics. Access to this zone must be tightly restricted, as any compromise here can affect production or safety. Further down the field or the IO zone include the sensor actuators and instrumentation that interface directly with the physical process. These devices often lack native security features, making segmentation and protocol filtering essential. Finally, the safety system, such as the SIS and the ESD controllers, remain physical and logically separated from standard control system. Their isolation ensures that the safety instrument function remain operational even if other zones are compromised. So overall, the IC 86243 zoning approach provides a clear framework for isolating asset, limiting lateral movement, and applying the right control at the right level. This segmentation model form a backbone of defensible ICS security architecture. Effective network segmentation is one of the most critical safeguard in an ICS environment because it restricts the lateral movement and ensure that the only authorized traffic can be reached to the sensitive control asset. The first of all, the strict firewall enforce clear boundaries between network zoning. This means the traffic is not only filtered by the IP and the port, but also the protocol and the directions. Segmentation start Segmentation should start with the positive security approach model, where all the traffic by default deny and permit only traffic which explicitly allowed for a particular port, protocol, and in a specific direction. And more importantly, no any policies on the firewall. Let's have a few examples to understand this concept. For example, you have been asked to allow communication between a SCADA server to the RTUs. The firewall policy should allow only the traffic from the SCADA server's IP address as a source and RTU's IP as a destination, with the destination port, let's suppose at 20,000, and a protocol is DNP3. Other than this, all communication between SCADA servers and the RTU should be blocked by default. Let's have another example of the communication between the SCADA server, HMI, engineering workstation to a specific PLC. The firewall policy should be configured in a way that permit the Modbus function 3 and 4 read codes from the HMI or a SCADA to a specific PLC only. And on the other hand, allow write code 8, 5, 6, 15, and 16 only in a maintenance window from an engineering workstation subnet. By doing this, this prevents accidental or malicious logical change during the production. There is a key point now, which we need to keep in our consideration. All the communication between the different zones should go through a firewall as their gateway. And there is no inter-VLAN routing or the layer 3 switch involved in this one. Because if you do like this, you can create a segmentation, but there is no use that you can control the security of these zones, because the routing happening between the layer 3 switches and not going through the firewalls. No direct access to the PLC communication. Corporate IT systems should never reach to PLC RTU directly under any circumstances. Instead, the communication must flow through a control intermediate system such as a historian application servers or a SCADA system placed in the DMZ. This prevents common IT threat from directly impacting automation devices. Let's suppose the MES in the IT should not talk to controller. Instead, the MES push workflow work order to the DMZ application broker. The broker synchronizes this with the SCADA in the operational zone, and which then orchestrate the changes to the PLC. PLC IP should not routable from the IT, so that any outbreak in the IT will not reach the controller. Similarly, corporate analytics access pipeline data only available via a replicated story in the DMZ. Analytics user never query controls on asset directly. This will help to eliminate the risk of analytic tools using unintended commands. Unidirectional gateway or the data diode. For the highly sensitive process, unidirectional gateway may be deployed. These hardware enforced one-way communication devices allow information such as process historian data to flow out of the control environment while blocking any inbound traffic. This ensures that even if the IT network is compromised, attacker cannot send back commands back to the control zone. And finally, the vendor access isolation. It is essential to managing a third-party connection. Vendor should connect only through a dedicated, time-bound, secure remote access gateway. And their session should be restricted to a specific equipment or a VLAN they are authorized to support. This prevents a vendor compromise become an entry point into the OT system. For example, a vendor connect to a dedicated remote access gateway in a DMZ using a multi-factor authentication, device process check, and a time-based approval. Their session land on a hardened OT jump server with a session recording. From their firewall rules allow access only to a required asset, no east-west access to the other skits. On the other hand, on-site a vendor laptop must be passed through a network access control and placed in a vendor VLAN. With ingress access to the jump servers only, internet access should be blocked, USB mesh storage is disabled, and file transfer happen through a scan staging shared in the DMZ. The account also enabled for just-in-time access and remain disabled by default or auto expire after change window. So overall segmentation ensures that each part of the ICS network is contained, controlled, and protected significantly, reducing the possibility that a single point of compromise can spread throughout the system. Industrial DMZ implementation. So industrial DMZ is a critical security layer within the ICS architecture because it creates a control buffer between the corporate IT network and the ICS environment. This separation ensures that there is two network never communicate directly. The services like storing, replication server, patch management, staging, antivirus update, distribution, remote access jump server, proxy server, NTP server, and the backup server, staging server must be reside in the DMZ, as all of these services should need to communicate with enterprise zone, and this separation will dramatically reduce the risk of an IT compromise propagating into the industrial control systems. Secure remote access. As we discussed earlier, secure remote access continue to be the one of the most targeted and the successful exploit entry point in the industrial control environment. Because attacker frequently leverage compromised credential, misconfigured VPNs, or a poorly monitored vendor connection as a path into the operation system. Securing remote access demands a rigorous control and multi-layer security strategy. For example, enforce a multi-factor authentication for all the remote connection because the password alone are not sufficient against the modern credential theft. Centralized access through a monitored intermediate host in the DMZ, which never expose to the control system directly. Implement just-in-time access. Vendor account should be disabled by default and enable only during the uh, approved window. VPN should be terminated in the enterprise or a DMZ layer only. Network access control for the on-site vendor machine and geo and IP restrictions, device posture check, and client attestation for the remote endpoints. File transfer hygiene, use a scan strategy area in the DMZ, block USBs, mass storage in a control zone. Asset inventory and the visibility is one of the most fundamental requirement in securing an ICS environment because you cannot protect what you cannot see. The most ICS networks still lack a complete and accurate inventory of all the devices connected to their control system. In many cases, plants have legacy equipment that have been added over a decade, undocumented network drops, vendor installed states, or a field devices that engineer assumes are isolated, but they are actually routable. Without clear visibility, it becomes nearly impossible to accurately assess the risk or detect threats. Passive monitoring, continuous discovery, traffic baselining, and a real-time change detection convert a black box OT network into an observable system. So the misconfiguration, vendor surprise, and advisory actions are caught before they become safety and production incident. So if we talk about the passive monitoring, modern security programs rely heavily on it. These tools observe the network traffic without generating active props, ensuring there is no risk to the disruption fragile PLC, RTU, and safety controllers. By simply listening the traffic at the span port and tap, they cannot identify they can identify devices, protocol, firmware versions, and communication patterns, and even vulnerabilities without interfering with the operations. Automatic discovery. Capab- Automatic discovery capability has built and maintain the continuous update asset inventory. The system automatically identifies new devices when they appear on the network, flag unknown assets, correlate them with the vendor signatures or the protocol fingerprints. For example, the tool might detect a newly connected engineering laptops, an HMI running outdated Windows patch, or a vendor PLC with unfamiliar firmware, all without requiring a manual scanning. So once this visibility is established, the next crucial step is to create a baseline normal traffic behavior. This includes the understanding which device is communicating with which other device, which port and protocol they are using, and the expected frequency and the direction of the traffic. For instance, it, it may baseline that the SCADA server pull PLC every 500 milliseconds, or that a certain field device should never initiate outbound connection. Any deviation from these patterns become an indicator of potential misconfiguration or compromise. With this baseline in place, the system can detect unauthorized changes in real time. This includes identifying unexpected firmware updates, new write commands, unusual Modbus and DNP3 function codes, configuration changes pushed to the PLC outside scheduled maintenance window, or unauthorized devices appearing on the network. These alerts provide early warning of both accidental issues and malicious activities before they escalate into the safety and the production incidents. Hardening of the ICS component, like a firewall, switch, PLCs, controllers, and engineering system is essential for reducing the overall attack surface within the ICS environment. Many industry devices ship with unnecessary services enabled default contention and open ports that are rarely used during the normal operations. Disabling unused ports and services such as the FTP, Telnet, and web interface or the vendor-specific management protocol greatly minimize the number of entry points an attacker can exploit. Using the signed and the validated firmware is equally important, ensuring that all the PLC, RTU, and the safety controllers only accept the firmware that are cryptographically signed by the vendors. Help prevent attacker from installing and modifying or malicious firmware images. This control directly mitigate threats where the adversaries try to implant backdoors or alter the device's behavior at the firmware levels. Another critical practice is to lock and secure the project file, including the ladder logics, function blocks, diagrams, configuration files, HMI project data. These engineering files should be stored in a control repositories with version controls, checksums, and strict access rights. Only authorized personnel should be able to modify or download the logics controls. Every change should follow a document management change process. Locking these files help prevent accidental edits, unauthorized logical changes, and tampering by compromised accounts. And finally, engineering workstation must be isolated and tightly controlled. This machine have highest privilege in the OT environment because they can modify control logics, deploy firmwares, and interact with safety system. For that reason, engineering workstation should be placed in dedicated network segment, not used for the general purpose, and protected with application whitelisting, multi-factor authentication, and hardened OS configuration. They should never serve as a dual-purpose IT/OT devices. Isolating these stations ensures that the malware from the IT system cannot reach critical configuration tool, and that only trusted engineer can access the programming environment. So overall, hardening the ICS component is about eliminating unnecessary exposure, validating device integrity, protecting the engineering data, and safeguarding the system that have the most direct control over the plant. Further, the component, the patch strategy. OT system requires a careful structure approach to patching, application control, and the system recoveries. Our robust patch strategy is essential, but unlikely IT environment and industrial system cannot be patched aggressively or without planning. Many SCADA servers, HMI or historian, and engineering workstation runs applications that are tightly coupled to the vendor certified OS versions. As a result, patch must be tested in a staging environment and deployed only during the control maintenance window to avoid unintended downtime and incompatibility issues. Application whitelisting is one of the most effective defense control in the ICS environment. Since OT system runs a small predictable set of the application, whitelisting ensures that only approved executable scripts and the libraries are allowed to run. This prevents the execution of malware, unauthorized tools, and unapproved engineering softwares. Even if attacker gain access to the system For example, a compromised user account cannot deploy a ransomware or execute a remote script if those binaries are not included in the approved list. Backup and recovery capabilities from is the last line of your defense. Every critical component, PLC, HMI, SCADA server, historian, switches, firewall, engineering project file must be scheduled and verified backup. And this backup must be stored online and the offline location. Backup need to be include and these backup need to be include even control logics, firmware versions, configuration files, system images, and database snapshot. Regular recovery testing equally important. Backup data is only useful if an organization can store it quickly and correctly during the incident. In the event of ransomware, hardware failure, or the unauthorized configuration change, reliable backup allow the plant to store automation system and resume the operation with minimal downtime. Monitoring and detection. Traditional IT tools fall short in industrial environment because they are not designed to interrupt the OT specific protocol. Command structure and device behavior to effectively detect threats in the ICS network. We need to monitor a system built with OT context and protocol awareness. OT-aware IDs and the IPS solution are specifically designed to understand the industrial protocol. These systems can inspect function codes, validate the command sequence, and flag unsafe operation, such as unauthorized write commands to the PLC, unexpected framework downloads, or a CSAS programming attempts. They are tuned to timing and sensitivity of the control network. Effective monitoring is also require a comprehensive log collection across the ICS environment. These logs must be normalized and retained in a centralized system where the security team can perform the analysis. Behavioral detection add another layer of defense by identifying deviation from the established baseline or the normal OT activity. Finally, the integration all monitoring feeds in a centralized SOC or SIM platform provide unified visibility across the environment. Identify abnormal activity at the earliest possible stage is one of the most critical elements of a strong defense posture. When the threats are detected quickly, security team can contain the issue and stop an incident for escalating further. Earlier visibility enable faster response, reduce operational impact, and significantly increase the chance of preventing a full-scale compromise. Compliance frameworks. Industry standard and the regulatory frameworks such as ISA 62443, NIST, NERC, ISO provide a structural foundation for building and managing security in the industrial control system environment. Each firmware offer guidance on areas like the network segmentation, access control, change management, system hardening, monitoring, and governance. They help the organization establish a consistent process, define security requirement, and align engineering practices with the cybersecurity best practices expectations. However, it is important to recognize that the compliance does not automatically equal the security. Many organizations successfully meet the audit requirement while still significantly gaps in their operational defense. Compliance frameworks typically define what must be achieved at a high level, but they do not prescribe all of the technical procedures or a real-time protection necessary to defend against the modern threats. For example, an environment may be compliant yet still have significant misconfigured PLC, insufficient monitoring, or outdated remote access controls. These firmwares, sorry, these should be referred as a strong starting point rather than end goals. The established baseline requirement, but truly security comes from going beyond checklist-based compliance, implementing continuous monitoring, real-world risk assessment, threat-informed defense, and the operational practices tailored to the unique demand of the industrial system. So let's we will discuss a lot of component security controls and strategies in our previous slides. So let's have a quick look on the modern ICS architecture, which was fully segmented and all the security has been applied. So in a mature ICS architecture, the environment built around a fully segmented model that follows established standards such as ISA 62443. The network is organized into clearly defined zone conduits, each separate based on function criticality, the trust level. This structure ensures that the system only communicates through a control pathway rather than freely across the network. There is a clear separation between the IT network and an adjusted DFZ, operational zone, control zone, and the safety system. Each zone has its own security control communication rules, access requirement. This prevents unnecessary direct communication between layers and minimize the risk at the that a compromise in the zone will affect another. Traffic crossing zone boundary is tightly controlled by the strict firewall rules, combining a deep packet inspection tailored for the OT protocol. Instead of relying solely on the port-based filtering, firewall actively inspect the industrial command to ensure that the only authorized and the safe functions, such as the read request or the approve polling, are allowed through. This adds a critical layer of protection against malicious or the unintended commands targeting the PLC. Remote access is also heavily secured. All external or the vendor access must be passed through a jump server, be authenticated with multi-factor authentication, and operate under a time-bound least privileged access window. This prevents persistence, uncontrolled remote connectivity, and provide complete visibility into all external activity touching the ICS environment. Continuous OT awareness monitoring and the anomaly detection provide a real-time visibility into the controller behavior, protocol actively, user action, and the system changes. Because ICS network are predictable and stable, deviations such as a new communication path, unusual write commands, or unexpected device behavior are detected quickly. Adjoining workstations are fully isolated from general network traffic and locked down with a strict access control. Application, a long list, and the patch governance, PLCs, controllers, and hardening ensure unused services are disabled. Firmware is validated and the project file is protected against the unauthorized modifications. The security benefit of this architecture are significant. Lateral movement across the ICS network is dramatically limited, making it difficult for a tracker or even internal errors to spread beyond their point of origin. Abnormal commands, unauthorized logic, downloads, or a sudden configuration change can be detected earlier because they cause operational impact. Even if the IT network is compromised, the ICS remain protected because multi-layer of the isolation and the inspection prevent threats from reaching control system. This mature security posture provides a strong foundation for a long-term cybersecurity resilience. It is it improves safety, maintain process integrity, and ensure operation can continue reliably even during the security incidents somewhere else in the enterprise. So when we talk about the secure ICS environment, so it is not a single point of one-time job. Secure ICS environment is a roadmap. It is important to understand this is the not a one-time project or the checklist. You complete one and walk away from it. It is a continuous process that begin with assessing the current environment, moving into the designing a secure architecture, and then implementing the required controls, and finally sustaining and improving those control over the time. Each phase feed into the next, ensuring security evolves as the ICS environment and the threat landscape change.